Welcome to the Whispering Universes channel, where tonight we embark on humanity's most profound journey beyond the very edge of time itself, into the ultimate mystery that has captivated minds since consciousness first gazed upward at the stars and dared to ask the deepest question of all: what came before the beginning of everything? As you settle into this moment, breathing slowly and deeply, prepare to explore the most fundamental mystery in all of existence. Tonight, we venture beyond the familiar boundaries of space and time, beyond matter and energy, beyond cause and effect themselves, to contemplate what might have existed before the Big Bang, or whether such a question even has meaning. We'll discover that the edge of our observable universe might not be the edge of everything, and that the beginning of our cosmic story might itself be just one chapter in an infinitely larger tale. The Big Bang represents the ultimate horizon of human knowledge, a cosmic boundary beyond which our most sophisticated theories break down and our deepest understanding fails. At this edge, 13.8 billion years ago, our observable universe emerged from conditions so extreme that density and temperature become infinite, space and time lose their familiar meanings, and the very concepts of before and after dissolve into mathematical impossibility. Yet this breakdown of knowledge, rather than ending our quest for understanding, opens up realms of possibility that stretch the limits of imagination. If physics fails at the moment of the Big Bang, what lies beyond that failure? If our universe had a beginning, what preceded that beginning? If time itself emerged with the Big Bang, what does it mean to ask what came before time existed? These questions thrust us into territory where science meets philosophy, where mathematics encounters the limits of logical reasoning, where the most rigorous thinking must grapple with concepts that seem to transcend human comprehension. Tonight, we'll explore the cutting-edge theories that attempt to pierce the veil of the ultimate beginning, from eternal inflation scenarios, where our Big Bang is just one bubble in an infinite foam of universes, to cyclic models where our cosmos endlessly repeats cycles of birth, death, and rebirth. We'll encounter ideas so strange they seem like science fiction. The possibility that our entire universe is a quantum fluctuation that spontaneously emerged from absolutely nothing, that reality itself might be a vast computation running on some cosmic computer, or that consciousness itself plays a fundamental role in bringing the physical world into existence. These aren't idle speculations, but serious proposals by leading physicists and cosmologists who have pushed their theories to the absolute limits of mathematical possibility. The quest to understand cosmic origins forces us to confront the most basic questions about existence itself. Why is there something rather than nothing? What makes the laws of physics the way they are? Could reality have been fundamentally different? Or are there deep principles that make our universe inevitable? Does the cosmos require an explanation, or might existence simply be a brute fact that needs no justification? These inquiries reveal the remarkable limits of human knowledge, while simultaneously showcasing the extraordinary power of human reason to approach the unapproachable. We are biological creatures, evolved on a small planet, orbiting an ordinary star, yet we have developed mathematical frameworks sophisticated enough to describe the behavior of matter and energy back to fractions of a second after the Big Bang. We can trace the cosmic evolution that led from primordial simplicity to the staggering complexity of galaxies, stars, planets, and life itself. But perhaps most remarkably, we have learned to recognize the boundaries of our knowledge with precision. Modern cosmology doesn't just tell us what we know about the universe, it tells us exactly where our knowledge ends and mystery begins. The Big Bang singularity represents such a boundary, a mathematical cliff beyond which our equations cease to function and our conceptual frameworks break down entirely. This recognition of limits is itself a profound achievement. For most of human history, people created stories to fill the gaps in their understanding, populating the unknown with gods, spirits, and mythological narratives that provided comfort but didn't truly explain anything. Modern science takes a different approach. It maps the territory of the known with extraordinary precision, clearly marking the borders where knowledge gives way to mystery. Tonight's exploration will take us to those borders and peer carefully into the darkness beyond. We'll discover that the question, what existed before the Big Bang, might be like asking, what is north of the North Pole? A question that seems sensible, but reveals deeper confusions about the nature of space, time, and existence itself. We'll see how this apparent meaninglessness opens up new ways of thinking about reality that are far stranger and more wonderful than any simple answer could provide. The theories we'll encounter range from the scientifically mainstream to the speculatively exotic, but all share a common thread. They represent serious attempts by brilliant minds to push beyond the apparent limits of human understanding. Some propose that our Big Bang was just one event in an eternal sequence of cosmic recycling. Others suggest that our universe is one bubble in an infinite multiverse, where every possible variation of physical law plays out simultaneously. Still others propose that reality itself is fundamentally computational, mathematical, or even conscious. As we explore these possibilities, we'll discover that they're not just abstract intellectual exercises, but ideas with profound implications for how we understand our place in existence. If our universe is just one of infinitely many, what does that mean for human significance? If reality is fundamentally mathematical, what does that say about the relationship between mind and matter? If consciousness plays a role in cosmic creation, how does that change our understanding of ourselves? These questions don't have easy answers indeed. They might not have answers at all in any conventional sense. But the journey of exploring them reveals something profound about the human condition. We are beings capable of asking questions that transcend the boundaries of our existence, of imagining possibilities that stretch beyond the limits of our experience, of finding beauty and meaning in mystery itself. Tonight, as we venture into the deepest unknown, we invite you to release any expectation of finding simple, definitive answers. Instead, allow yourself to be carried by the currents of wonder and possibility, to rest in the profound mystery of existence itself. The greatest truth we might discover is that some questions are more beautiful than any answer could be, and that the capacity to ask such questions is itself one of the most remarkable features of a universe that somehow gave birth to minds capable of contemplating their own cosmic origins. Let the gentle currents of cosmic mystery carry you forward as we begin our journey to the very edge of everything. In the winter of 1927, a Belgian priest and physicist named Georges Lemaitre published a paper that would fundamentally transform humanity's understanding of cosmic history. His hypothesis of the primeval atom suggested that the entire universe had emerged from an initial state of extraordinary density and temperature, a cosmic egg that exploded to create space, time, matter, and energy in a singular moment of creation. This radical idea, initially ridiculed by many scientists, including Albert Einstein, would eventually become the Big Bang theory, one of the most successful scientific frameworks ever developed. Lemaitre's insight emerged from his careful analysis of Einstein's general relativity equations, which had revealed that the universe could not be static, it must be either expanding or contracting. While Einstein himself was initially uncomfortable with this implication and introduced the cosmological constant to maintain a static universe, Lemaitre embraced the dynamic nature of space-time and followed the mathematics to its logical conclusion. If the universe is expanding now, it must have been denser in the past, ultimately tracing back to a state of infinite density at a definite moment in cosmic history. The observational foundation for the Big Bang theory came through the work of Edwin Hubble in the late 1920s. Using the powerful telescopes at Mount Wilson Observatory, Hubble measured the distances to nearby galaxies and discovered that they were moving away from us at velocities proportional to their distances. This relationship, known as Hubble's law, provided direct evidence for cosmic expansion and allowed astronomers to calculate backwards to determine when the expansion began, approximately 13.8 billion years ago. But the true triumph of Big Bang theory came through its successful predictions about the cosmic microwave background radiation. In 1948, Ralph Alpher and Robert Herman realized that if the universe had emerged from a hot, dense state, it should have cooled as it expanded, leaving behind a faint afterglow of thermal radiation that would still be detectable today. When Arno Penzias and Robert Wilson accidentally discovered this radiation in 1965, it provided smoking gun evidence for the Big Bang theory and earned them the Nobel Prize. The cosmic microwave background represents the earliest light in the universe, photons that were released when the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms about 380,000 years after the Big Bang. Before this epoch of recombination, the universe was opaque to light, filled with hot plasma that scattered photons continuously. The moment when this plasma cleared represents the farthest back in time that we can directly observe with electromagnetic radiation. Big Bang nucleosynthesis provides another remarkable confirmation of the theory. During the first few minutes after the Big Bang, when the universe was hot and dense enough to support nuclear reactions, protons and neutrons combined to form the light elements: hydrogen, helium, lithium, and their isotopes. The predicted abundances of these elements match observations with extraordinary precision, providing strong evidence that the universe did indeed emerge from an extremely hot, dense state. The timeline of cosmic evolution that emerges from Big Bang theory is both detailed and precise. At 10 circumflex -43 seconds after the beginning, the Planck time quantum effects of gravity become important, and our current understanding of physics breaks down. Between 10 circumflex -36 and 10 circumflex -32 seconds, cosmic inflation causes exponential expansion that solves several puzzles about the universe's large-scale structure. By 1 second after the Big Bang, the universe has cooled enough for stable nuclei to form. After 380,000 years, atoms form, and the cosmic microwave background is released. Hundreds of millions of years later, the first stars ignite, beginning the process of cosmic structure formation that continues today. Yet for all its successes, the Big Bang theory contains a profound limitation that becomes clear when we trace cosmic evolution backwards toward the beginning. As we approach t=0, the density and temperature of the universe increase without bound, eventually reaching values that are formally infinite. At this moment, the Big Bang singularity, the equations of general relativity, break down completely, providing no description of what happened at or before this instant. This singularity represents more than just a mathematical inconvenience. It marks a fundamental boundary to the reach of physical theory. All the conservation laws that govern energy, momentum, and other physical quantities trace back to this point and can provide no information about what might have preceded it. The elegant mathematical framework that describes cosmic evolution from fractions of a second after the Big Bang forward becomes meaningless when applied to the singularity itself. The horizon problem illustrates one of the puzzles that the standard Big Bang model struggles to address. Regions of the universe that are now separated by vast distances and could never have been in causal contact, nevertheless have nearly identical temperatures, as measured in the cosmic microwave background. Without some mechanism to establish thermal equilibrium across regions that could never exchange information, this uniformity seems miraculous. Similarly, the flatness problem emerges from the observation that the geometry of space appears to be almost perfectly flat, balanced precisely between the curved geometries that would lead to either immediate recollapse or runaway expansion. The standard Big Bang model provides no explanation for why the initial conditions of the universe should have been so carefully fine-tuned to produce this critical geometry. The monopole problem arises from grand unified theories that predict the production of exotic particles called magnetic monopoles in the early universe. These particles should be abundant in the cosmos today, yet they have never been observed. The standard Big Bang model cannot explain their absence without invoking special initial conditions. These problems hint that the Big Bang theory, despite its remarkable successes, may be incomplete. The singularity that marks the beginning of cosmic evolution in this model might not represent the ultimate beginning of everything, but rather the breakdown of our current theoretical framework. Understanding what lies beyond this breakdown requires new physics that can describe the quantum nature of gravity and space-time itself. The triumph of Big Bang theory lies not just in its successful description of cosmic evolution, but in its clear delineation of the boundaries of our knowledge. By precisely mapping what we understand about cosmic history and clearly identifying where that understanding breaks down, the theory provides a roadmap for future investigations into the deepest mysteries of existence. The singularity that limits the theory's reach backward in time becomes an invitation to develop new frameworks that might pierce the veil of ultimate cosmic origins. As we contemplate the remarkable success of Big Bang theory in describing 13.8 billion years of cosmic evolution, we're reminded that even our most successful theories have limits. The ultimate question of what preceded the Big Bang requires us to venture beyond these limits into territory where physics meets philosophy and mathematics encounters mystery. At the heart of the Big Bang theory lies a mathematical crisis so profound that it threatens the very foundations of physical understanding. The singularity, that moment of infinite density and temperature that marks the beginning of cosmic time, represents more than just an inconvenient mathematical artifact. It signals the complete breakdown of our most successful theories about the nature of reality, forcing us to confront the disturbing possibility that the universe emerged from conditions that cannot be described by any physical law we understand. The singularity emerges inevitably from the equations of general relativity when we trace the expansion of the universe backwards in time. As we approach t=0, the scale factor of the universe, which describes the relative size of space itself, shrinks towards zero. This means that all the matter and energy currently distributed throughout cosmic space becomes compressed into a region of vanishing volume, creating densities and temperatures that grow without bound toward mathematical infinity. When physicists encounter infinities in their calculations, it usually signals that something has gone wrong with their theoretical framework. Infinite quantities cannot be measured, cannot be compared with other quantities, and cannot be used to make predictions about physical processes. An infinite density would create gravitational effects so strong that they would overwhelm every other force in nature. An infinite temperature would mean that particles possess infinite kinetic energy, violating the fundamental conservation laws that govern physical interactions. The mathematical pathology of the singularity becomes even more apparent when we consider what general relativity actually describes. Einstein's theory is fundamentally a theory of space-time geometry. It tells us how matter and energy curve the fabric of space and time, and how this curvature in turn affects the motion of matter and energy. But at the singularity, this geometric description breaks down completely. Space and time themselves become infinitely curved, losing any recognizable meaning as the stage upon which physical processes occur. The problem extends beyond just mathematical inconvenience to challenge the very notion of physical law itself. Science assumes that the behavior of the universe can be described by consistent mathematical relationships that remain valid under all circumstances. But the singularity represents a point where all such relationships fail simultaneously. There is no equation that can describe infinite density, no physical law that governs the behavior of matter under such extreme conditions, no conceptual framework that can encompass such a state. Roger Penrose and Stephen Hawking proved in the 1960s that singularities are not just artifacts of special symmetric models, but arise inevitably in general relativity under very general conditions. Their singularity theorems demonstrate that any universe containing matter and governed by Einstein's equations must contain singularities points, where the geometric description of space-time breaks down completely. These theorems suggest that the Big Bang singularity is not an accident of particular assumptions, but a fundamental feature of relativistic cosmology. The Planck epoch, which extends from t=0 to approximately 10 circumflex negative 43 seconds after the Big Bang, represents the domain where quantum effects of gravity become important. During this earliest period, the universe was so small and dense that quantum mechanical uncertainty in the position and momentum of particles extended to cosmic scales. The familiar distinction between space and time, matter and energy, cause and effect, would have been blurred beyond recognition. At the Planck scale, which characterizes the size and duration of quantum gravitational effects, space and time themselves might become discrete rather than continuous. Instead of the smooth geometric manifold described by general relativity, space-time might have a granular, foam-like structure where the very concepts of distance and duration lose their usual meanings. In such a regime, the smooth evolution described by classical physics gives way to quantum superpositions of different geometric possibilities. The quest to understand physics beyond the singularity has driven the development of quantum gravity theories that attempt to merge general relativity with quantum mechanics. String theory proposes that the fundamental constituents of reality are not point particles, but extended objects, vibrating strings, whose dynamics might avoid the infinities that plague point particle theories. Loop quantum gravity suggests that space and time themselves are quantized, made up of discrete units that cannot be subdivided further. These approaches offer tantalizing hints that the Big Bang singularity might not represent a true beginning, but rather a transition point, where our classical description of spacetime gives way to some more fundamental quantum description. In string theory scenarios, the apparent singularity might mark a point where the geometry of space undergoes a dramatic transformation, possibly connecting our expanding universe to a pre-existing contracting phase. Loop quantum gravity models suggest that the singularity might be replaced by a quantum bounce, where a collapsing universe rebounds to create our observed expansion. The interpretation of the singularity also depends on subtle questions about the relationship between mathematical models and physical reality. Some physicists argue that the singularity is merely an indication that general relativity has reached the limits of its applicability, like a map that becomes useless when you try to use it in territories it was never designed to describe. From this perspective, the singularity doesn't represent a physical state, but rather the breakdown of our theoretical description. Others suggest that the singularity might be physically real, but fundamentally unknowable, representing a boundary beyond which information cannot flow into our observable universe. If the laws of physics themselves emerged with the Big Bang, then asking what preceded these laws might be like, asking what caused the axioms of mathematics, a question that transcends the framework within which meaningful answers can be formulated. The measurement problem in quantum mechanics adds another layer of complexity to singularity physics. If the universe began in a quantum superposition of all possible states, what caused this superposition to collapse into the specific reality we observe? Some interpretations suggest that observation itself plays a role in determining which quantum possibilities become actual, raising profound questions about the relationship between consciousness and cosmic evolution. Attempts to resolve the singularity problem often lead to even stranger possibilities. Some models suggest that our Big Bang might have been preceded by a previous universe that collapsed to a maximum density before rebounding. Others propose that the singularity might be avoided through higher dimensional effects that redirect gravitational collapse in ways not apparent in our three-dimensional experience. Still others suggest that the universe might have emerged through quantum tunneling from a state of pure nothingness. The ethical and existential implications of the singularity problem extend far beyond technical physics. If the beginning of the universe cannot be described by physical law, what does this say about the nature of explanation itself? Are there aspects of reality that fundamentally transcend scientific understanding? Does the universe require some form of creation that lies outside the natural order? Or might ultimate existence simply be a brute fact that needs no justification? As we grapple with the profound mysteries posed by the Big Bang singularity, we discover that the limits of physics might themselves be telling us something important about the nature of reality. In the early 1980s, a young physicist named Alan Guth made a discovery that would revolutionize our understanding of cosmic origins. While studying the behavior of matter in the extremely early universe, Guth realized that a brief period of exponential expansion, lasting perhaps 10 circumflex negative 32 seconds, could solve several major puzzles about cosmic structure while providing a natural mechanism for generating the Big Bang itself. This inflationary epoch represents one of the most remarkable chapters in cosmic history, a cosmic startup phase that transformed microscopic quantum fluctuations into the seeds of galaxies and set the stage for everything we observe in the universe today. Goethe's insight emerged from his study of grand unified theories, which attempt to describe how the fundamental forces of nature, electromagnetic, weak nuclear, and strong nuclear, might have been unified at extremely high energies. These theories predict that as the universe cooled from its initial state, it would undergo phase transitions similar to water freezing into ice, but involving the fundamental structure of space-time itself. During one such transition, the universe might become trapped temporarily in a false vacuum state, a condition of higher energy density that creates repulsive gravitational effects. The physics of this false vacuum state leads to extraordinary consequences. Unlike ordinary matter, which creates attractive gravitational effects that slow cosmic expansion, the false vacuum generates negative pressure that drives exponential expansion. During the inflationary epoch, the universe doubles in size every 10 circumflex, negative 37 seconds or so, growing by a factor of at least 10 circumflex, 26 inches, less than 10 circumflex, negative 32 seconds. This means that a region initially smaller than a proton expands to larger than a grapefruit in this incredibly brief interval. The horizon problem, which had puzzled cosmologists for decades, finds elegant resolution through inflation. The cosmic microwave background shows remarkable uniformity across the entire sky, yet according to standard Big Bang theory, widely separated regions of the universe could never have been in causal contact to establish thermal equilibrium. Inflation solves this puzzle by proposing that all observable regions of the universe were indeed in causal contact before inflation began, when they were confined to a microscopic volume. The exponential expansion then stretched these causally connected regions to cosmic scales while preserving their thermal equilibrium. Similarly, the flatness problem dissolves under inflation's influence. Observations indicate that the geometry of space is remarkably close to perfectly flat balanced, precisely between positive and negative curvature. This represents an extraordinary fine-tuning in standard Big Bang models, since any significant deviation from flatness would grow rapidly as the universe expands. Inflation resolves this puzzle through a geometric effect. Any curved surface appears flat when viewed from sufficiently close range. The exponential expansion of inflation stretches any initial curvature to such enormous scales that our observable universe appears flat, just as the surface of Earth appears flat to local observers, despite its global spherical geometry. The monopole problem also finds resolution through inflation. Grand unified theories predict that exotic particles called magnetic monopoles should have been produced abundantly in the early universe and should be detectable today. The fact that no monopoles have ever been observed had threatened these theories until inflation provided an explanation. If monopoles were produced before inflation began, the exponential expansion would dilute their density to undetectable levels throughout our observable universe. Perhaps most remarkably, inflation provides a natural mechanism for generating the density fluctuations that seeded cosmic structure formation. Quantum mechanical uncertainty ensures that the inflaton field, the field responsible for driving inflation, cannot have perfectly uniform energy density. These quantum fluctuations get stretched to macroscopic scales during inflation, creating tiny variations in density that persist after inflation ends. When inflation finally terminates and the false vacuum decays into ordinary matter and radiation, these density variations become the seeds from which galaxies, stars, and planets eventually form. The mathematical elegance of this process is breathtaking. Microscopic quantum events, normally confined to subatomic scales, get amplified through inflation to provide the initial conditions for cosmic structure formation. The largest structures in the universe, galaxy clusters spanning hundreds of millions of light years, can trace their origins to quantum fluctuations that occurred when the universe was smaller than an atomic nucleus. This represents a direct connection between the quantum mechanical and cosmological realms that few theoretical frameworks can match. Observational evidence for inflation has grown steadily stronger over the decades since Guth's original proposal. The cosmic microwave background shows exactly the pattern of temperature fluctuations that inflation predicts, with a nearly scale invariant spectrum of density perturbations that matches detailed theoretical calculations. The overall geometry of space appears flat to high precision, consistent with inflation's predictions. Even the gravitational waves that inflation should produce might be detectable in the polarization patterns of the cosmic microwave background. However, inflation also raises profound new questions about cosmic origins. If inflation can solve the puzzles of the standard Big Bang model, what caused inflation itself to begin? The inflationary process requires very special initial conditions, a patch of false vacuum large enough and uniform enough to undergo sustained exponential expansion. But such conditions seem just as unlikely as the fine-tuned initial conditions that inflation was designed to explain. Eternal inflation, proposed by physicists like Andrei Linde and Alexander Vilenkin, offers a partial resolution to this puzzle, while raising even deeper questions. If inflation can begin in one region of space, quantum fluctuations ensure that it will begin in other regions as well. Some regions will exit inflation quickly and form universes like ours, while others will continue inflating and spawn new inflationary regions. This process never ends, creating an infinite fractal structure of universe, creating inflation that has no beginning and no end. In the eternal inflation scenario, our Big Bang represents not the beginning of everything, but merely the local end of inflation in our particular cosmic neighborhood. The question, what came before the Big Bang, transforms into what happens in the eternally inflating space from which our universe emerged. This answer is both more satisfying and more vertiginous than traditional approaches. It avoids the problems of absolute beginnings while positing an infinite multiverse that transcends all our familiar concepts of space, time, and causation. The implications of inflation for cosmic origins extend far beyond solving technical problems in cosmology. If inflation can create universes from quantum fluctuations, it suggests that the emergence of space, time, matter, and energy might be far more natural than we previously imagined. Rather than requiring miraculous fine-tuning or divine intervention, cosmic creation might be an inevitable consequence of physical law operating in regimes we are only beginning to understand. As we contemplate this remarkable period of cosmic acceleration that lasted less than a trillionth of a trillionth of a trillionth of a second, yet shaped the entire structure of observable reality, we begin to appreciate how the deepest truths about cosmic origins might lie not in the moment of ultimate beginning, but in the physical processes that transform microscopic possibility into macroscopic actuality. In the strange realm of quantum mechanics, even empty space is not truly empty. The vacuum, what we might naively think of as pure nothingness, seethes with activity at microscopic scales, filled with virtual particles that pop into existence and annihilate in timeframes so brief that they cannot be directly observed, yet whose effects can be measured with extraordinary precision. This quantum vacuum might hold the key to understanding how something can emerge from nothing, how the universe itself might have crystallized out of pure possibility through mechanisms that transcend our everyday understanding of cause and effect. The foundation of quantum vacuum physics lies in Heisenberg's uncertainty principle, which states that we cannot simultaneously measure certain pairs of properties like position and momentum, or energy and time, with arbitrary precision. This principle implies that the energy of any system, even apparently empty space, cannot be exactly zero. Instead, the quantum vacuum contains zero-point energy, a residual energy that remains even when all thermal motion has been removed and no particles are present. This zero-point energy manifests through quantum fluctuations, spontaneous appearances of particle-antiparticle pairs that borrow energy from the vacuum, exist for brief moments, allowed by the uncertainty principle, and then annihilate to repay their energy debt. These virtual particles are not directly observable, but their effects create measurable phenomena, like the Casimir force, where two parallel metal plates placed close together in vacuum experience an attractive force due to the exclusion of virtual particles between them. The energy density of the quantum vacuum should, according to naive calculations, be enormous, possibly infinite. When quantum field theorists add up the zero-point energies of all possible particle fields, they obtain values that are 10 circumflex, 120 times larger than the observed energy density of our universe. This represents the largest discrepancy between theory and observation in all of physics, suggesting either that our understanding of quantum vacuum physics is fundamentally flawed, or that some unknown mechanism cancels out most of the vacuum energy. Yet despite these theoretical difficulties, the quantum vacuum provides a natural mechanism for the spontaneous creation of matter and energy. If vacuum fluctuations can create virtual particles that quickly annihilate, what prevents these fluctuations from occasionally creating real particles that persist? Under extreme conditions near the event horizons of black holes, during rapid expansion of space, or in the presence of strong gravitational fields, virtual particles can become real through processes that modern physics describes with mathematical precision. The concept of vacuum metastability adds another layer of complexity to quantum vacuum physics. Just as water can exist in a supercooled state below its freezing point before suddenly crystallizing into ice, the vacuum might exist in a false state of apparent stability, while a lower energy true vacuum state remains possible. If our universe currently occupies such a false vacuum, it might spontaneously tunnel to the true vacuum through a quantum process that would fundamentally alter the laws of physics. This possibility raises profound questions about the stability of physical law itself. The masses of particles, the strengths of forces, and even the number of spatial dimensions might be determined by which vacuum state the universe currently occupies. A transition to a different vacuum could transform physics so completely that atoms would dissolve, chemistry would become impossible, and the entire structure of matter and energy would reorganize according to new principles. The many worlds interpretation of quantum mechanics provides one framework for understanding how quantum fluctuations might relate to cosmic origins. If every quantum event causes reality to branch into multiple parallel worlds, corresponding to different possible outcomes, then vacuum fluctuations might constantly create new universes. Each virtual particle pair that appears in the vacuum might represent a branching point, where reality splits into versions where the particles become real and versions where they annihilate as expected. From this perspective, our universe might be just one branch in an infinite tree of quantum possibilities, distinguished from neighboring branches only by the particular pattern of vacuum fluctuations that happen to become real rather than remaining virtual. The Big Bang might represent not a unique cosmic beginning, but rather one quantum event among countless others, special to us only because we exist within the branch where it occurred. The role of observation in quantum mechanics adds another mysterious element to vacuum physics. According to some interpretations, quantum systems exist in superpositions of multiple states until observation causes them to collapse into definite configurations. If this principle applies to vacuum fluctuations, then the act of observation might play a role in determining which virtual particles become real, which vacuum states become actualized, and which quantum possibilities evolve into physical reality. This possibility raises vertiginous questions about the relationship between consciousness and cosmic creation. If observation participates in the transition from quantum possibility to physical actuality, and if the universe emerged from quantum vacuum processes, then consciousness might play a fundamental role in cosmic evolution. The universe might not just have evolved observers through random processes. Observers might participate in creating the universe through their participation in quantum measurement processes. Quantum tunneling provides another mechanism through which the vacuum might spontaneously create universes. Just as particles can tunnel through energy barriers that they classically could not cross, entire universes might tunnel into existence from states of pure nothingness. The probability of such tunneling events might be extremely small, but in an infinite expanse of potential space and time, even infinitesimally unlikely events occur infinitely often. Recent developments in quantum field theory have revealed even more exotic possibilities for vacuum-driven cosmic creation. Theoretical frameworks like eternal inflation suggest that quantum fluctuations in vacuum energy can drive exponential expansion that creates pocket universes with different physical properties. Each bubble universe emerges from quantum processes in the vacuum, develops its own space and time, and potentially gives rise to further bubbles through continued quantum fluctuations. The relationship between quantum mechanics and gravity remains one of the deepest unsolved problems in physics, but progress in this area might illuminate how vacuum processes could create space-time itself, rather than just matter and energy within pre-existing space. If space and time are themselves quantum mechanical phenomena that emerge from more fundamental quantum processes, then the quantum vacuum might be the birthplace not just of particles, but of the geometric arena within which all physics unfolds. As we contemplate the seething activity of the quantum vacuum, we begin to appreciate how the boundary between something and nothing might be far more subtle than our everyday experience suggests. The vacuum is not empty nothingness, but rather a pregnant void filled with infinite potential, constantly creating and destroying, offering glimpses of realities that might have been while providing the foundation for the reality that is. Among all the mysteries surrounding cosmic origins, perhaps none is more profound than the remarkable fine-tuning of physical constants that makes our universe capable of supporting complexity, structure, and ultimately, life itself. The fundamental parameters that govern physics, the masses of particles, the strengths of forces, the expansion rate of space, appear to be calibrated with extraordinary precision to values that allow atoms to form, stars to shine, and chemical evolution to proceed. This cosmic Goldilocks effect raises one of the deepest questions in all of science. Is this fine-tuning evidence of design, cosmic coincidence, or something far stranger? The anthropic principle, first articulated by physicist Brandon Carter in the 1970s, provides a framework for thinking about this apparent fine-tuning by recognizing that we necessarily observe a universe compatible with our existence. The weak anthropic principle simply notes that we shouldn't be surprised to find ourselves in a universe that permits observers, since universes without observers have no one to notice their existence. This seems obvious, but its implications reach deep into questions about cosmic origins and the nature of physical law. Consider the remarkable precision required for stellar nucleosynthesis, the process by which stars forge the heavy elements essential for planets and biology. Fred Hoyle discovered, in the 1950s, that carbon production in stellar cores depends on a precise resonance in the carbon nucleus that allows 3 helium nuclei to combine efficiently. If this resonance were shifted by even a few percent, carbon would be far too rare for complex chemistry, and life as we know it would be impossible. Hoyle was so struck by this apparent coincidence that he declared it evidence for a superintellect that had monkeyed with physics. The list of such fine-tunings extends throughout physics. If the strong nuclear force were slightly stronger, all hydrogen would have fused into heavier elements during the Big Bang, leaving no fuel for stars. If it were slightly weaker, atomic nuclei could not form, and only hydrogen would exist. The electromagnetic force requires similar precision, stronger, and electrons would be bound so tightly to nuclei that chemistry becomes impossible, weaker, and atoms become too large to participate in complex molecular structures. Perhaps most remarkably, the cosmological constant, the energy density of empty space itself, appears to be fine-tuned to a precision of 1 part in 10 circumflex 120. This represents the most extreme fine-tuning known in physics. If this constant were much larger, space would expand so rapidly that galaxies could never form. If it were much smaller but negative, the universe would collapse before stars could ignite, The observed value seems to be precisely calibrated to allow for cosmic structure formation and long-term stability. The strong anthropic principle goes beyond mere observation to suggest that the universe must have properties that allow observers to develop within it at some stage. This stronger version verges on teleological thinking, the idea that the universe is somehow directed toward the production of consciousness. Most scientists are uncomfortable with this interpretation because it seems to require purpose or design that transcends natural processes. The multiverse provides an elegant resolution to fine-tuning problems without invoking supernatural design. If our universe is just one member of a vast ensemble containing all possible combinations of physical constants, then we naturally find ourselves in one of the rare universes where the constants happen to permit complexity and life. The vast majority of universes in such an ensemble would be sterile and lifeless, but among infinite possibilities, some would inevitably have the right combination of properties to support observers. Eternal inflation provides a concrete mechanism for generating such a multiverse. As different regions of space exit inflation at different times and with different properties, they create bubble universes with different physical constants. Most bubbles would have physics incompatible with structure formation, but scattered throughout the infinite inflationary expanse would be rare bubbles like ours, where conditions permit complexity and consciousness. String theory adds another dimension to multiverse fine-tuning solutions. The theory predicts approximately 10 circumflex, 500 different ways to configure the extra dimensions, each corresponding to a different set of particle masses and force strengths. If eternal inflation explores all these possibilities, creating universes with every possible combination of string theory parameters, then anthropic selection naturally explains why we observe constants compatible with life. However, the anthropic approach faces significant challenges. The measure problem, determining how to assign probabilities to different outcomes in an infinite multiverse, remains unsolved. Some anthropic predictions seem to conflict with observations, suggesting that conscious observers should be more common in universes quite different from ours. The approach also raises philosophical questions about whether anthropic reasoning constitutes genuine scientific explanation or merely shifts the mystery to a higher level. Observer selection effects add complexity to anthropic reasoning. If consciousness can arise in multiple forms throughout a multiverse, we should expect to find ourselves as typical observers rather than special ones. Some analyses suggest that most conscious beings in a multiverse would be Boltzmann brains, random quantum fluctuations that create consciousness with false memories rather than evolved beings with genuine histories. This leads to the disturbing possibility that we are more likely to be such random observers than genuine products of cosmic evolution. The relationship between fine-tuning and consciousness raises profound questions about the nature of mind itself. If the universe seems calibrated for the emergence of observers, what role might consciousness play in cosmic evolution? Some interpretations of quantum mechanics suggest that consciousness participates in the collapse of quantum superpositions, potentially affecting the physical development of reality. Could the apparent fine-tuning of physical constants reflect some fundamental connection between mind and matter? The temporal aspects of anthropic reasoning also deserve consideration. Why do we find ourselves existing during this particular epoch of cosmic history, when stars are still shining and planets can support life? The universe will spend the vast majority of its future in a cold, dark state where no new structure formation occurs. From a purely probabilistic perspective, we should expect to exist during the far future when most observers have ever lived. Yet we clearly exist during a special period of cosmic fertility. Recent attempts to calculate anthropic probabilities have yielded surprising results. Some analyses suggest that we should expect to live in a universe with a slightly larger cosmological constant than observed, or with somewhat different particle masses. The fact that these predictions don't match observations exactly either supports the anthropic approach by confirming that we live in a rare but possible universe, or challenges it by suggesting that the reasoning leads to wrong conclusions. As we contemplate the remarkable fine-tuning that allows our existence, we're forced to choose between three basic options: incredible cosmic coincidence, supernatural design, or a vast multiverse that makes our apparently special universe inevitable. Each option carries profound implications for our understanding of cosmic origins and our place in the larger scheme of existence. As we push deeper into the implications of inflation theory, we encounter one of the most remarkable and vertiginous ideas in modern cosmology: the possibility that inflation, once begun, never truly ends. Eternal inflation suggests that the process that created our universe continues forever, spawning an infinite hierarchy of bubble universes, each with potentially different physics, in an ever-expanding fractal structure that transcends all our familiar notions of space, time, and cosmic uniqueness. This framework transforms the question, what came before the Big Bang, into something far stranger. What is happening in the eternal inflationary space from which our universe emerged? The concept of eternal inflation emerged from detailed studies of how the inflationary process might end. In simple models, inflation terminates uniformly when the inflaton field reaches the bottom of its potential energy curve, causing exponential expansion to cease, and the field's energy to convert into the matter and radiation of the hot Big Bang. But more realistic models reveal that inflation doesn't end everywhere simultaneously. Quantum fluctuations ensure that some regions exit inflation while others continue expanding exponentially. The key insight is that inflation creates space faster than it can terminate. Even though inflation ends in some regions, the ongoing exponential expansion produces new space, where inflation continues at a rate that exceeds the rate at which regions exit inflation. This means that the total volume of inflating space grows without bound, while regions like our observable universe represent only tiny, finite bubbles within an infinite sea of eternal expansion. To visualize this process, imagine a pot of boiling water where bubbles of steam form and rise to the surface. Each bubble represents a region where inflation has ended and a new universe has formed, while the surrounding water represents the eternally inflating space. But unlike bubbles in water, cosmic bubbles can never touch each other because the space between them expands faster than light can travel. Each bubble universe exists in permanent isolation, unable to communicate with or influence its neighbors. The mathematical description of eternal inflation reveals its profound implications for cosmic origins. If inflation is eternal into the future, then it likely has no beginning in the past either. The process might have been occurring forever, with no first moment when inflation began. This eliminates the need for special initial conditions to start inflation. If the process is eternal, it has always been happening and always will be. Different bubble universes can have radically different physical properties, depending on how the inflaton field behaves in different regions. As inflation ends in each bubble, the field can settle into different vacuum states, each corresponding to different particle masses, force strengths, and even numbers of spatial dimensions. This creates a cosmic landscape of possibilities where every allowed combination of physical laws is realized somewhere in the infinite ensemble. The string theory landscape provides a concrete realization of this idea. String theory predicts approximately 10 circumflex, 500 different ways to configure the extra dimensions, each giving rise to different four-dimensional physics. If eternal inflation explores all these possibilities, it creates a multiverse containing every possible form of string theory physics. Our universe, with its particular combination of particle masses and force strengths, represents just one random point in this vast landscape of possibilities. Anthropic selection provides a natural explanation for why we observe our particular combination of physical constants. Among the infinite variety of bubble universes created by eternal inflation, only a tiny fraction will have physics compatible with the formation of atoms, molecules, stars, planets, and ultimately life. We necessarily find ourselves in one of these rare bubbles, not because our physics is special in any objective sense, but because only universes with life-compatible physics can give rise to observers capable of measuring physical constants. The concept of time becomes peculiar in eternal inflation scenarios. Different bubble universes have their own internal time coordinates that begin with their individual Big Bang events. But the eternally inflating space that contains all bubbles might exist in a kind of eternal present where duration has no meaning. The question of what happened before our Big Bang dissolves, because before and after only have meaning within individual bubble universes, not in the timeless realm of eternal inflation. The measure problem represents one of the most challenging aspects of eternal inflation theory. In an infinite multiverse containing every possible type of observer in infinite quantities, how do we calculate probabilities for different observations? The usual methods of statistical reasoning break down when dealing with infinite sets of possibilities. Different mathematical approaches to the measure problem can yield contradictory predictions about what types of observations should be typical. Some proposed solutions to the measure problem focus on cutoff procedures that count observers in finite spacetime regions. Others attempt to weight different types of observers by their complexity or the likelihood of their evolutionary histories. Still others suggest that the measure problem reveals fundamental limitations in our ability to make predictions about infinite multiverses. The lack of consensus on this issue represents one of the major theoretical challenges facing eternal inflation models. Observational tests of eternal inflation remain challenging because we can only observe our own bubble universe directly. However, the theory makes some testable predictions about the properties our universe should have. The cosmic microwave background should show specific patterns of temperature fluctuations. The geometry of space should be flat, and gravitational waves from inflation might leave detectable signatures in the polarization of background radiation. More exotic observational possibilities include searching for the signatures of bubble collisions. If our bubble universe collided with another bubble during its early expansion, this collision might leave circular patterns in the cosmic microwave background. Several research groups have searched for such signatures, with some claiming tentative detections and others finding no convincing evidence. The implications of eternal inflation for human meaning and cosmic purpose are profound and unsettling. If infinite universes contain every possible configuration of matter and energy, then every possible life, every possible choice, every possible outcome occurs infinitely many times throughout the multiverse. This suggests either that individual choices and experiences are infinitely important because they occur in infinite contexts, or completely meaningless because they represent infinitesimal fractions of infinite possibility. The temporal structure of eternal inflation also raises questions about cosmic purpose and direction. If the process has no beginning and no end, with new universes constantly forming throughout infinite time, then there is no ultimate goal toward which cosmic evolution aims, and no final state that represents completion or perfection. The multiverse simply is, generating infinite novelty and infinite repetition in equal measure. As we contemplate this vision of eternal cosmic creativity, infinite universes bubbling into existence throughout endless time and space, we begin to appreciate how the question of what came before the Big Bang might dissolve into something far stranger, the recognition that before and after might be provincial concepts that only apply within individual universes, while the larger reality transcends all our familiar categories of temporal sequence and causal ordering. Long before modern cosmology discovered the expansion of the universe, ancient cultures intuited that time itself might be cyclical rather than linear. Hindu cosmology envisioned endless cycles of creation and destruction spanning billions of years. Greek philosophers contemplated eternal recurrence, where identical events repeat throughout infinite time. These ancient insights into cosmic cycles have found new mathematical expression in modern theories that propose our Big Bang was not a unique beginning, but one event in an endless sequence of cosmic renewals that has been occurring forever and will continue eternally. The appeal of cyclic models lies partly in their ability to avoid the philosophical problems associated with absolute beginnings. If the universe oscillates through infinite cycles of expansion and contraction, then there was no first moment when time began, and no need to explain what caused the initial creation. Instead of emerging from nothing, Each cycle emerges from the preceding cycle through physical processes that can be described mathematically and potentially observed. The simplest cyclic model involves a universe that expands from a Big Bang, reaches maximum size, then contracts back to a big crunch, before bouncing into a new expansion phase. This oscillating universe model was popular in the mid-23th century as an alternative to the standard Big Bang cosmology. However, detailed calculations revealed serious problems with this approach. Each cycle would increase the universe's entropy, causing successive cycles to become longer and more dilute until the oscillations eventually stopped. Modern cyclic models have overcome these thermodynamic problems through more sophisticated approaches, inspired by string theory and higher dimensional physics. The ekpyrotic scenario, proposed by Neil Turok, Paul Steinhardt, and others, suggests that our three-dimensional universe exists on a moving membrane, or brane, in higher dimensional space. Periodic collisions between branes create the appearance of Big Bang events in our dimensions, while avoiding the singularities that plague traditional cyclic models. In the ekpyrotic framework, what we call the Big Bang represents a collision between our brane and a parallel brane moving through higher dimensional space. This collision generates the hot, dense conditions that characterize the early universe, while simultaneously creating the density fluctuations that seed structure formation. After the collision, the branes separate, our universe expands and cools, and structures form just as in standard cosmology. But eventually, the branes begin approaching each other again, leading to another collision and another cycle. The mathematical elegance of this approach lies in its ability to solve many of the puzzles that motivated inflation theory through completely different mechanisms. The horizon problem disappears because our brane existed in a stable state before the collision, allowing thermal equilibrium to establish across all regions that would later become causally disconnected by the collision. The flatness problem resolves because the collision creates flat geometry regardless of initial conditions. Density fluctuations arise naturally from quantum effects in the higher dimensional space. Loop quantum gravity provides another framework for cyclic cosmology that avoids singularities through the quantization of space and time themselves. In this approach, space consists of discrete units that cannot be compressed beyond a minimum size. When matter density reaches the maximum value allowed by quantum geometry, gravitational attraction reverses to become gravitational repulsion, causing a collapsing universe to bounce into expansion. This big bounce replaces the Big Bang singularity with a smooth transition between contraction and expansion phases. The information preservation properties of cyclic models offer potential solutions to deep puzzles in cosmic evolution. In eternal inflation scenarios, the infinite creation of new universes seems to violate information conservation principles, with new information constantly appearing from nowhere. Cyclic models avoid this problem because the total information content remains constant across cycles, with information from previous cycles potentially encoded in the initial conditions of subsequent cycles. Some cyclic models suggest that physical constants and laws might evolve from cycle to cycle, creating a form of cosmic natural selection where only universes with stable, long-lived cycles persist. This could explain the apparent fine-tuning of physical constants without requiring infinite multiverses or supernatural design. Constants that allow long-lived universes would tend to persist through many cycles, while those leading to rapid collapse or runaway expansion would be selected against. The observational signatures of cyclic cosmology differ significantly from those predicted by inflation theory. Rather than the nearly scale-invariant spectrum of density fluctuations that inflation produces, cyclic models predict a more complex pattern that might be detectable in precision measurements of the cosmic microwave background. The gravitational wave signatures of cyclic models also differ from inflation, potentially providing observational tests that could distinguish between these competing frameworks. Recent observations have placed constraints on some cyclic models while leaving others viable. The detection of primordial gravitational waves would strongly favor inflation over many cyclic alternatives, since gravitational wave production differs significantly between these approaches. However, the absence of detected gravitational waves doesn't rule out cyclic models and might even support them if they predict lower gravitational wave amplitudes. The philosophical implications of cosmic cycles extend far beyond technical cosmology. If the universe repeats eternally, then every moment, every choice, every experience has occurred infinitely many times before and will occur infinitely many times again. This cosmic version of eternal recurrence raises profound questions about the uniqueness and meaning of individual existence. Are we living through events for the first time, or are we eternal actors repeating identical performances throughout infinite time? The relationship between cycles and consciousness poses particularly intriguing questions. If information passes between cycles, could conscious experiences from previous cosmic epochs influence subsequent cycles? Some speculative proposals suggest that advanced civilizations might find ways to encode information about their existence into the structure of space-time itself, allowing their influence to persist across cosmic cycles and potentially guide the evolution of consciousness in future epochs. The temporal structure of cyclic cosmology also challenges conventional notions of progress and purpose. In linear time models, cosmic evolution has a direction from simple to complex, from homogeneous to structured, from unconscious to conscious. But in cyclic models, this apparent progress is temporary. All complexity eventually dissolves in cosmic contractions, only to emerge again in subsequent expansions. This suggests either that progress is an illusion, or that it operates on scales larger than individual cycles. Some variants of cyclic cosmology attempt to preserve progress through mechanisms that allow complexity to increase from cycle to cycle. Information about the development of structure and consciousness might accumulate across cycles, leading to a cosmic learning process where each cycle builds upon the achievements of its predecessors. This would combine the eternal nature of cyclic models with the purposeful direction that many find necessary for cosmic meaning. As we contemplate these visions of endless cosmic renewal, we begin to appreciate how cyclic models transform the question of cosmic origins from what came before the beginning to what patterns persist through endless repetition. The answer might lie not in finding the first moment, but in understanding the eternal processes that generate endless moments of beginning. In the deepest mathematical explorations of reality's foundations, string theory emerges as perhaps humanity's most ambitious attempt to understand the ultimate nature of existence. This framework proposes that the fundamental constituents of reality are not point particles, but tiny, vibrating strings, whose different oscillation patterns create all the particles and forces we observe. When applied to cosmic origins, string theory reveals possibilities so strange they challenge our most basic concepts about the beginning of everything, suggesting that our universe might be one slice of a higher dimensional reality where the Big Bang represents just one event in a vast symphony of cosmic creation. String theory's journey began in the late 1960s as an attempt to understand the strong nuclear force, but it quickly evolved into something far more ambitious, a theory of everything that could unify quantum mechanics with general relativity. The key insight is that when particles are modeled as extended objects, rather than mathematical points, many of the infinities that plague quantum field theory cancel out, potentially providing finite descriptions of quantum gravity and other fundamental interactions. But string theory's most profound implications for cosmology emerge from its requirement for extra spatial dimensions. The mathematics of string theory only works consistently in 10 or 11 dimensions, far more than the 3 spatial dimensions we observe. This suggests either that string theory is wrong, or that these extra dimensions are somehow hidden from our direct experience. The standard explanation is that the extra dimensions are compactified, curled up so tightly at every point in space that we cannot detect them with current technology. The landscape of string theory reveals the cosmic implications of dimensional compactification. There are approximately 10 circumflex 500 different ways to curl up the extra dimensions, each corresponding to a different four-dimensional physics. These different compactifications give rise to different particle masses, force strengths, and even different numbers of particle types. From this perspective, the physical laws we observe represent just one possibility among an almost infinite variety of alternatives. M-theory, developed in the 1990s as a more complete formulation of string theory, introduces even more exotic possibilities for cosmic origins. In M-theory, fundamental objects include not just strings, but higher dimensional membranes, or brands, that can extend through multiple spatial dimensions. Our observable universe might exist on a three-dimensional brane embedded in higher dimensional space, with gravity able to leak into the extra dimensions, while other forces remain confined to our brane. The ekpyrotic scenario emerges naturally from M-theory brane cosmology. If our universe exists on a brane moving through higher dimensional space, then collisions between branes could create the conditions we observe as the Big Bang. These brane collisions generate enormous amounts of energy while avoiding the singularities that plague traditional Big Bang models. The collision creates hot, dense matter on our brane, while simultaneously producing the density fluctuations that seed cosmic structure formation. Pre-Big Bang scenarios in string cosmology suggest that our universe existed in a very different state before the apparent beginning of expansion. String theory permits solutions where time extends infinitely into the past, with the Big Bang representing a transition between two phases of cosmic evolution rather than an absolute beginning. These models describe a universe that evolves from a cold, empty state through a heating phase that produces the hot, dense conditions of the Big Bang. The landscape problem represents one of the most challenging aspects of string theory cosmology. With 10 circumflex 500 different possible compactifications, string theory makes no unique predictions about the physics we should observe. Instead, it suggests that all possible combinations of physical laws are realized somewhere in a vast multiverse. This transforms physics from a search for unique mathematical truth into an exploration of which possibilities are compatible with the existence of observers. Anthropic reasoning becomes essential in the string landscape because we can only observe universes compatible with our existence. Among the vast number of possible string theory vacua, only a tiny fraction will have physics that allows atoms to form, stars to shine, and life to evolve. We find ourselves in one of these rare habitable universes, not because string theory predicts our specific physics, but because only universes with life-compatible physics can give rise to observers capable of studying string theory. The hierarchy problem finds potential resolution in string theory through mechanisms that determine why some forces are much stronger than others. In higher dimensional string models, the apparent weakness of gravity might result from its ability to spread into extra dimensions, while other forces remain confined to our brane. This provides a geometric explanation for the enormous differences in force strengths without requiring fine-tuning of fundamental parameters. Quantum corrections in string theory can drive cosmic evolution in ways that differ significantly from standard cosmology. The dilaton field, which determines the strength of string interactions, can evolve dynamically and drive periods of cosmic expansion or contraction. These string-specific mechanisms might provide alternatives to inflation for solving the horizon and flatness problems while generating different observational signatures. The duality symmetries of string theory reveal deep connections between apparently different physical theories. These dualities suggest that what appears to be different physics in different regions of the landscape might actually be equivalent descriptions of the same underlying reality. This raises profound questions about the nature of physical law itself. Are the differences between various string vacua real, or do they represent different perspectives on a single, more fundamental structure? Higher dimensional black holes in string theory can have properties dramatically different from their four-dimensional counterparts. These objects might serve as bridges between different regions of the landscape, allowing transitions between universes with different physics. If our universe formed from the decay of a higher dimensional black hole, This could explain both our cosmic origins and the specific combination of physical constants we observe. The role of supersymmetry in string cosmology provides constraints on possible cosmic histories. Supersymmetric string models require equal numbers of bosonic and fermionic particles, but we observe no such symmetry in nature. This suggests either that supersymmetry is broken in our universe or that we exist in a non-supersymmetric region of the landscape. Understanding how supersymmetry breaking occurs might provide clues about why our universe has its particular properties. Recent developments in string theory have revealed connections to other approaches to quantum gravity. The ADS, divided by CFT correspondence, shows that string theory in curved spacetimes can be equivalent to quantum field theories on the boundary of those spacetimes. This holographic principle suggests that the physics of cosmic origins might be encoded in boundary information rather than bulk dynamics, providing new perspectives on the relationship between space, time, and information. As we contemplate the vast landscape of possibilities that string theory reveals, we begin to appreciate how cosmic origins might transcend our familiar three-dimensional perspective. The Big Bang might represent not the beginning of everything, but rather one event in a higher dimensional symphony of cosmic creation, where the deepest truths about existence operate according to principles we are only beginning to glimpse. While string theory attempts to resolve the mysteries of cosmic origins by proposing that fundamental reality consists of vibrating strings in higher dimensions, loop quantum gravity takes a radically different approach. It suggests that space and time themselves are quantized, made up of discrete units that cannot be subdivided further. This framework leads to one of the most elegant solutions to the Big Bang singularity problem ever proposed, the Big Bounce, where our expanding universe emerges not from a singular moment of infinite density, but from the collapse and rebound of a previous cosmic epoch. Loop quantum gravity emerged from attempts to apply the principles of quantum mechanics directly to Einstein's general relativity without invoking extra dimensions or exotic new particles. The key insight is that if matter and energy are quantized into discrete packets, then the space-time geometry that responds to matter and energy should also be quantized. This leads to a picture where space consists of tiny loops or nodes connected by links, forming a quantum geometric network at the smallest possible scales. The discreteness of quantum geometry has profound implications for cosmic evolution. In classical general relativity, matter can be compressed to arbitrarily high densities, leading to singularities where physical laws break down. But in loop quantum gravity, there is a maximum possible density beyond which further compression becomes impossible. When matter reaches this quantum geometric limit, gravitational attraction automatically reverses to become gravitational repulsion, causing a contracting universe to bounce into expansion. This Big Bounce scenario eliminates the mathematical infinities that plague the Big Bang singularity, while preserving all the successful predictions of standard cosmology. The universe still expands from a hot, dense state, undergoes nucleosynthesis to create light elements, and cools to allow structure formation. The only difference is that this expansion phase was preceded by a contraction phase from a previous cosmic epoch, with the bounce occurring when quantum geometric effects became dominant. The mathematical framework of loop quantum gravity reveals why the bounce is inevitable rather than just possible. The quantum geometric constraints that prevent space from shrinking below a minimum size operate automatically, without requiring special initial conditions or fine-tuning of parameters. This represents a fundamental difference from classical scenarios where bounces require carefully constructed matter properties or exotic equations of state that might not exist in nature. Information preservation through the bounce provides one of the most intriguing aspects of loop quantum gravity cosmology. Unlike the Big Bang singularity, which destroys all information about previous states, the Big Bounce allows information to pass from the contracting phase to the expanding phase. This means that the initial conditions of our observable universe might encode information about the structure and evolution of the previous cosmic epoch. The observational signatures of a Big Bounce could potentially be detected in precision cosmological observations. The passage of information through the bounce would create subtle correlations in the cosmic microwave background that differ from those predicted by inflation theory. These signatures might appear as specific patterns in temperature fluctuations or anomalous correlations between widely separated regions of the sky. Quantum geometric effects near the bounce also provide natural explanations for several puzzles in standard cosmology. The horizon problem resolves because regions that appear causally disconnected in our expansion phase were actually in causal contact during the previous contraction phase. The flatness problem disappears because the quantum geometric repulsion that drives the bounce naturally creates flat spatial geometry regardless of initial conditions. The generation of primordial density fluctuations in loop quantum gravity differs significantly from inflation scenarios. Rather than arising from quantum fluctuations in a scalar field, density perturbations in bouncing models can emerge from the quantum geometric fluctuations of space itself near the bounce. These fluctuations get amplified during the transition from contraction to expansion, creating the seeds for cosmic structure formation. Numerical simulations of the Big Bounce have revealed the detailed dynamics of how quantum geometric effects operate during the transition between contraction and expansion. These calculations show that the bounce occurs smoothly over a finite time interval, with the contracting universe reaching a minimum size before expanding again. The duration of the bounce depends on the matter content and quantum geometric parameters, but typically occurs over timescales comparable to the Planck time. The relationship between loop quantum gravity and other approaches to quantum gravity remains an active area of research. While string theory and loop quantum gravity make different assumptions about the fundamental nature of space-time, some researchers have found connections between these frameworks that might eventually lead to a unified understanding of quantum geometric effects. Black hole physics in loop quantum gravity provides additional insights into how quantum geometric effects might operate in extreme gravitational environments. The theory predicts that black holes have quantized areas and can only absorb matter in discrete chunks. When black holes evaporate through Hawking radiation, they might undergo quantum transitions that preserve information about their formation history. The polymer quantization techniques used in loop quantum gravity can be applied to other cosmological scenarios beyond the Big Bounce. These methods might resolve singularities in black hole formation, provide alternatives to cosmic inflation, or explain the observed acceleration of cosmic expansion through quantum geometric effects that become important at large scales. Recent developments in loop quantum gravity have explored the possibility of multiple bounces throughout cosmic history. If the universe undergoes repeated cycles of expansion and contraction, each separated by a quantum bounce, then cosmic evolution might be cyclic on the largest scales while remaining compatible with the observed evidence for linear cosmic evolution over the past 13.8 billion years. The philosophical implications of the Big Bounce extend beyond technical cosmology to questions about the nature of time and cosmic purpose. If our universe emerged from the quantum rebound of a previous cosmic epoch, then cosmic history extends infinitely into the past through an endless sequence of bounces. This eliminates the need for an absolute beginning while preserving the possibility of cosmic direction and progress. The role of consciousness in quantum gravity remains controversial, but some interpretations of loop quantum gravity suggest that observation might play a role in determining which quantum geometric configurations become actualized. If consciousness participates in quantum measurement processes that affect space-time geometry, then observers might influence cosmic evolution through quantum gravitational effects. As we contemplate the elegant mathematics of quantum geometry and the natural emergence of cosmic bounces from the discreteness of space and time, we begin to appreciate how the question of cosmic origins might be resolved not by transcending physics, but by understanding physics more deeply. The Big Bounce suggests that the universe never began because it never needed to begin. It simply is, eternal and self-generating through the quantum geometric processes that govern the deepest levels of reality. As our understanding of cosmic origins has deepened, we've discovered that the question, what came before the Big Bang, might be fundamentally transformed by an even more profound realization. Our universe might be just one member of an infinite ensemble of universes, each with different properties, laws, and histories. The multiverse concept suggests that rather than asking what preceded our cosmic beginning, we should ask why we find ourselves in this particular universe among countless alternatives, and whether the process that generates universes might itself provide mechanisms for cosmic selection that explain the remarkable properties we observe. The mathematical universe hypothesis, proposed by cosmologist Max Tegmark, represents perhaps the most radical form of multiverse thinking. According to this idea, every mathematically consistent structure exists as a physical reality, and what we call the physical universe is simply the mathematical structure we happen to inhabit. From this perspective, the question of cosmic origins becomes a question about mathematical existence. Why do mathematical structures exist? And why do we find ourselves embedded in this particular mathematical framework rather than another? This hypothesis suggests that the distinction between mathematics and physics is artificial. Rather than mathematics describing a pre-existing physical reality, mathematics is physical reality. Every possible equation, every geometric structure, every logical system that can exist without contradiction corresponds to an actual universe populated by observers for whom those mathematical relationships constitute the laws of nature. Our universe, with its specific combination of quantum mechanics, relativity, and thermodynamics, represents just one mathematical structure among infinitely many. Cosmic natural selection provides a different approach to multiverse theory that attempts to explain why universes might have properties conducive to complexity and life. Proposed by physicist Lee Smolin, this idea suggests that universes reproduce through black hole formation, with each black hole giving birth to a new universe with slightly modified physical constants. This creates an evolutionary process where universes that produce many black holes are more likely to have offspring, leading to the selection of physical constants that favor black hole formation. The remarkable observation is that the same physical constants that allow black hole formation also tend to permit the existence of stars, planets, atoms, and ultimately life. If cosmic natural selection operates through black hole reproduction, it might explain why we observe a universe with properties conducive to complexity without requiring fine-tuning or intelligent design. We live in a universe descended from successful reproducers in the cosmic evolutionary tree. Black hole cosmology extends this idea by proposing that our entire universe might have formed from the interior of a black hole in a higher dimensional parent universe. When matter collapses to form a black hole, extreme gravitational effects might create new space and time that expand into a full universe with different physical properties. This process could continue indefinitely, creating a fractal hierarchy of universes within universes, each generation potentially developing different laws of physics. The string theory landscape provides yet another framework for cosmic selection operating within a vast multiverse. With approximately 10 circumflex, 500 different ways to configure the extra dimensions, string theory admits an enormous variety of possible four-dimensional physics. If eternal inflation explores all these possibilities, creating bubble universes with every possible combination of string theory parameters, then anthropic selection naturally explains why we observe constants compatible with structure, formation, and life. In this landscape scenario, most universes would be sterile, unable to form atoms, molecules, or any complex structures. But scattered throughout the infinite ensemble would be rare universes with physics that permits complexity. We find ourselves in one of these rare habitable universes, not because our physics is objectively special, but because only universes with observer-compatible physics can give rise to beings capable of measuring physical constants and asking questions about cosmic origins. The measure problem represents one of the deepest challenges facing multiverse theories. In an infinite ensemble containing every possible type of observer in infinite quantities, how do we calculate probabilities for different observations? Traditional statistical reasoning breaks down when dealing with infinite sets, and different mathematical approaches to the measure problem can yield contradictory predictions about what we should expect to observe. Some proposed solutions involve cutoff procedures that count observers within finite spacetime regions. Others attempt to weight different types of observations by their complexity or information content. Still, others suggest that the measure problem reveals fundamental limitations in our ability to make predictions about infinite systems. The lack of consensus on this issue remains one of the major theoretical obstacles to accepting multiverse explanations for cosmic properties. The Boltzmann brain problem illustrates how multiverse reasoning can lead to counterintuitive conclusions. In an infinite multiverse with unlimited time and space, random thermal fluctuations will occasionally create brains with memories and consciousness identical to ours, but without genuine histories. If such random observers vastly outnumber evolved observers like ourselves, we would be more likely to be Boltzmann brains with false memories than genuine products of cosmic evolution. This possibility forces us to confront unsettling questions about the reliability of our experiences and memories. If most conscious observers in a multiverse are random fluctuations rather than evolved beings, then our apparent memories of a coherent history, extending back through childhood, human civilization, and cosmic evolution, might be illusions created by chance arrangements of matter. The very reasoning that leads us to postulate multiverses might itself be based on false memories implanted by random processes. Advanced civilizations might play active roles in cosmic selection if they develop the ability to create or influence universe formation. Some speculative proposals suggest that sufficiently advanced beings could trigger the formation of new universes through black hole creation, high-energy experiments, or manipulation of vacuum states. If such cosmic engineering becomes possible, then universe properties might reflect the preferences and values of their creators rather than blind physical processes. The simulation hypothesis represents an extreme form of cosmic selection, where advanced civilizations create simulated universes for research or entertainment purposes. If most conscious observers exist within simulations rather than base reality, then cosmic selection operates through the choices of simulation creators rather than fundamental physical processes. The properties we observe might reflect the research interests or aesthetic preferences of beings whose nature we cannot imagine. Information theoretic approaches to cosmic selection focus on how information is processed and preserved across different types of universes. Universes that can store, process, and transmit information efficiently might be more likely to generate observers capable of understanding their cosmic context. This could explain why we observe a universe with physical laws that permit complex computation and information storage. As we contemplate these various mechanisms for cosmic selection operating across infinite ensembles of possibilities, we begin to appreciate how the question of cosmic origins might be inseparable from questions about cosmic purpose and direction. Perhaps universes don't just happen randomly, but emerge through processes that naturally select for complexity, consciousness, and the capacity for self-understanding. In the most radical departure from traditional physics yet proposed, digital physics suggests that reality itself might be computational, that the universe operates not as a collection of particles and fields, obeying differential equations, but as a vast information processing system, executing a cosmic algorithm. This perspective transforms the question of cosmic origins from what came before the Big Bang to who or what is running the simulation and what prompted them to initiate the computation that we experience as physical reality. The computational view of nature emerged from the recognition that many physical processes can be modeled perfectly by computational systems. Cellular automata, simple programs, where cells on a grid update their states based on the states of neighboring cells, can generate incredibly complex patterns that resemble turbulence, crystal growth, biological development, and even the large-scale structure of the universe. If such simple computational rules can reproduce the behavior of complex physical systems, perhaps physical systems are themselves computational in nature. Stephen Wolfram's investigations into cellular automata revealed that extremely simple rules can generate patterns of unlimited complexity. Some cellular automata exhibit behavior that appears random, despite being completely deterministic, while others create structures that grow, interact, and evolve in ways that mirror biological and physical processes. This suggests that the apparent complexity of the natural world might emerge from the execution of relatively simple computational rules operating at a fundamental level. The it from bit hypothesis, proposed by physicist John Wheeler, represents an early version of digital physics thinking. Wheeler suggested that information is the fundamental substance of reality, with matter and energy emerging as secondary phenomena from underlying information processing operations. From this perspective, physical particles are not substantial objects, but rather information patterns that maintain coherence through computational processes. Quantum mechanics provides natural support for computational views of reality. The quantum state of a system can be represented as information. Quantum operations can be viewed as information processing, and quantum measurement can be understood as information extraction. The recent development of quantum computers demonstrates that quantum mechanical systems can indeed perform computations, suggesting that the universe might be a vast quantum computer processing information according to the rules of quantum mechanics. Digital spacetime theories propose that space and time themselves are discrete rather than continuous, with the universe consisting of a three-dimensional grid of computational cells that update according to simple rules. This discrete structure would naturally resolve many of the infinities that plague quantum field theory, while providing a computational framework for understanding quantum gravity. The Planck length and Planck time would represent the pixel size and clock speed of the cosmic computer. The simulation hypothesis represents the most direct application of digital physics to cosmic origins. If our universe is indeed computational, it might be a simulation running on some vast computer system created by advanced beings in a higher-level reality. These beings might be studying the development of intelligence, testing scientific theories, or simply entertaining themselves by observing the evolution of virtual worlds populated by conscious entities. Nick Bostrom's simulation argument provides a probabilistic framework for evaluating the likelihood that we live in a simulation. If some civilizations develop the computational power to run realistic simulations of conscious beings, and if they choose to run many such simulations, then simulated beings would vastly outnumber non-simulated beings in the total population of conscious entities. We might therefore be more likely to be simulated than real. The computational requirements for simulating a universe like ours are staggering but not necessarily impossible for sufficiently advanced civilizations. A Type 2 civilization with access to stellar-scale energy resources could potentially support computational systems sophisticated enough to simulate billions of conscious beings living in realistic virtual environments. The entire observable universe might be running on a computer no larger than a planet in the base reality. However, perfect simulation of quantum mechanics appears to require exponential computational resources, making complete universe simulation computationally intractable, even for advanced civilizations. This has led to proposals for optimization techniques that simulation creators might use, rendering only observed regions in full detail, using approximations for unobserved processes, or employing compression algorithms that maintain apparent realism while reducing computational load. The nested simulation possibility raises vertiginous questions about the levels of reality. If we are simulated beings created by advanced civilizations, those civilizations might themselves be simulated by even more advanced beings. This could continue indefinitely, creating infinite hierarchies of simulated realities with no clear base level. The question of cosmic origins would then become, what started the first simulation in the hierarchy, and how many levels deep are we? Glitch detection has become a cottage industry among those who take the simulation hypothesis seriously. Proposed signatures of simulated reality include apparent pixelation at the smallest scales of space and time, computational shortcuts that manifest as fundamental constants, speed of light limits that prevent information processing from overwhelming the simulation's computational capacity, and quantum mechanics itself as a compression algorithm that avoids computing all properties of particles simultaneously. The role of consciousness in digital physics raises profound questions about the nature of simulated experience. If consciousness can emerge from sufficiently complex information processing, then simulated beings with appropriate computational structures would have genuine subjective experiences indistinguishable from those of non-simulated beings. This means that simulated suffering and simulated joy would be as morally significant as their non-simulated counterparts. The fine-tuning problem finds potential resolution in simulation scenarios. Rather than requiring cosmic coincidences or vast multiverses to explain why physical constants permit complexity in life, but simulation theory suggests that our universe's parameters were deliberately chosen by programmers who wanted to study the development of complexity and consciousness. We observe a life-friendly universe because we exist within a simulation designed specifically to support life. Experimental tests of the simulation hypothesis remain challenging because a perfect simulation would be indistinguishable from reality to its inhabitants. However, some researchers have proposed experiments that might detect the discrete structure of simulated spacetime or reveal computational limits in physical processes. The Large Hadron Collider and other high-energy experiments might reveal pixelation effects if they probe scales where the simulation's computational grid becomes apparent. The programmer problem represents one of the deepest questions raised by simulation theory. Who or what created the simulation, and what are their motivations? If we are simulated beings, our creators might be biological entities like ourselves, artificial intelligences, evolved descendants of biological civilizations, or forms of consciousness so alien that we cannot imagine their nature or purposes. Recent developments in artificial intelligence and virtual reality have made simulation scenarios seem less like science fiction and more like plausible technological trajectories. As our own simulations become more sophisticated and our AI systems more capable, we can begin to imagine the endpoints of these developments. Perfect virtual worlds, populated by artificial beings who experience their simulated environments as completely real. As we contemplate the possibility that our entire reality might be a vast computation executing on some cosmic computer system, we're forced to reconsider fundamental assumptions about the nature of existence, consciousness, and purpose. Perhaps the deepest question is not what came before the Big Bang, but what prompted someone to press the cosmic run button that initiated the computation we experience as physical reality. As we probe ever deeper into the mysteries of cosmic origins, we encounter perhaps the most fundamental puzzle of all, the nature of time itself. Our question, what existed before the Big Bang, assumes that time is a universal backdrop against which events unfold, extending infinitely into the past and future. But modern physics suggests something far stranger, that time itself might be an emergent property that arose with the universe, making the very concept of before meaningless in the context of cosmic origins. Tonight, we explore the possibility that time is not fundamental, but constructed, not eternal, but created, not absolute, but relative to the very existence it appears to measure. The classical conception of time, inherited from Newton and common sense, treats time as an absolute framework, a universal clock that ticks uniformly throughout space, providing a cosmic now that divides past from future everywhere in the universe simultaneously. In this view, asking what came before the Big Bang is perfectly sensible. Time exists independently of physical events, so there must have been temporal moments before the first physical moment, even if nothing was happening during those moments. Einstein's special and general relativity shattered this absolute conception of time, revealing that temporal measurements depend on motion and gravitational fields. Time runs slower for objects moving at high speeds and in strong gravitational fields. There is no universal now events that are simultaneous for one observer occur at different times for observers in relative motion. Most fundamentally, space and time are not separate entities, but form a unified space-time continuum that can be curved, stretched, and dynamically evolved by matter and energy. When Einstein's equations are applied to cosmology, they reveal that space-time itself began expanding with the Big Bang. This suggests that time, as a dimension of space-time, came into existence with the universe rather than pre-existing as a container for cosmic events. If time began with the Big Bang, then asking what happened before the Big Bang is like asking what is north of the North Pole. The question contains a category error that reveals confusion about the nature of the concepts involved. Quantum mechanics introduces additional complexities to our understanding of time. In the quantum realm, the sharp distinction between past and future becomes blurred. Quantum superposition allows particles to exist in multiple states simultaneously until measurement forces them to choose definite properties. The act of measurement in the present can retroactively determine which quantum history actually occurred, suggesting that the past might not be fully determined until observed from the future. The Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe, contains no explicit time parameter. This timeless formulation of quantum cosmology suggests that the universe exists in a superposition of all possible configurations, with time emerging only when we consider specific observational perspectives within this eternal quantum state. From this view, time is not fundamental, but represents how conscious observers parse their experience of an underlying timeless reality. Imaginary time represents one of the most counterintuitive concepts in modern cosmology. Stephen Hawking proposed that we can understand cosmic origins by rotating the time coordinate into imaginary numbers, creating a four-dimensional space without temporal direction. In this Euclidean approach, the Big Bang singularity gets smoothed out into a regular geometric surface, like the South Pole on a sphere. The question of what came before the Big Bang disappears, because there is no before in a four-dimensional space that has no temporal direction. The emergence of time from timeless physics might occur through several mechanisms. Some theories suggest that time crystallizes out of quantum gravitational fluctuations, like ice forming from water. Others propose that time emerges through the accumulation of quantum entanglement between different regions of space. Still others suggest that time appears only when matter and energy create sufficient complexity to support thermodynamic processes that define temporal direction. The arrow of time, our universal experience, that time flows from past to future, presents another deep mystery. The fundamental laws of physics are largely time-symmetric. They work equally well whether time runs forward or backward. Yet we experience a clear temporal direction, from ordered past to disordered future, from memory to anticipation, from cause to effect. This psychological and thermodynamic arrow of time might emerge from special initial conditions at the cosmic beginning, rather than fundamental temporal asymmetry. Information theory provides new perspectives on the nature of time and its relationship to cosmic origins. If time emerges from the processing of information, then temporal flow might represent the universe computing its own evolution. Each moment would correspond to a step in a vast calculation, with the arrow of time pointing in the direction of increasing computational complexity. From this perspective, asking what came before the Big Bang is like asking what came before the first step of a calculation. The question assumes a temporal framework that doesn't exist outside the computation itself. Eternal inflation scenarios suggest that different regions of the multiverse might have different relationships to time. While individual bubble universes have their own internal time coordinates, the eternally inflating space that contains all bubbles might exist in a kind of eternal present where temporal duration has no meaning. Our cosmic time began with our local Big Bang, but this beginning occurred within a timeless inflationary background that has no beginning or end. Loop quantum gravity proposes that time itself is discrete rather than continuous, composed of individual moments separated by Planck scale intervals. This digital time would naturally resolve many puzzles about temporal continuity, while suggesting that our smooth experience of temporal flow emerges from averaging over enormous numbers of discrete temporal events. The Big Bang would represent not the first moment of continuous time, but the first frame in a cosmic movie composed of discrete temporal pixels. The relationship between consciousness and time remains one of the deepest mysteries in science and philosophy. Our subjective experience of temporal flow, the feeling that moments pass and that we move from past to future, might not correspond to any objective feature of physical reality. Instead, consciousness might create the illusion of temporal passage by comparing different brain states and constructing narratives about change and continuity. Some interpretations suggest that consciousness plays an active role in the creation of time through quantum measurement processes. If conscious observation participates in the collapse of quantum superpositions, then awareness might help determine which quantum possibilities become actualized in time. This would make consciousness a participant in temporal creation rather than just a passive observer of temporal flow. The possibility that time itself might be an illusion forces us to reconsider fundamental assumptions about existence and causation. If the universe exists eternally in a timeless quantum superposition, with temporal experience emerging only from particular observational perspectives, then questions about cosmic beginnings and endings might be based on misconceptions about the nature of existence itself. As we contemplate the possibility that time is not fundamental but emergent, we begin to appreciate how the question of cosmic origins might transcend temporal categories entirely. Perhaps what we call the Big Bang represents not a moment in time but the perspective from which time itself becomes visible, the observational stance that transforms timeless existence into temporal experience. At the very heart of all questions about cosmic origins lies the most profound puzzle that consciousness has ever encountered. Why is there something rather than nothing? This question cuts deeper than any inquiry about the Big Bang, deeper than any theory about multiverses or quantum fluctuations, deeper than any mathematical framework we might construct to describe reality. It confronts us with the ultimate mystery of existence itself, the staggering fact that anything exists at all when the default state of affairs would seem to be absolute nothingness. The question, why is there something rather than nothing, appears simple on its surface, but every word conceals layers of philosophical complexity. What exactly do we mean by something? Are we referring only to material objects, or does the category include abstract entities like numbers, logical relationships, and possibilities themselves? What constitutes nothing? Is it merely the absence of matter and energy, or does it extend to the absence of space, time, physical laws, and even logical principles? Different definitions of nothingness lead to radically different versions of the fundamental question. The weakest form of nothingness might simply be empty, space a vacuum devoid of particles, but still containing the potential for quantum fluctuations and virtual particle creation. In this interpretation, asking why there is something rather than nothing becomes a question about why empty space contains matter and energy, rather than remaining perpetually vacant. A stronger conception of nothingness would eliminate not just matter and energy, but space and time themselves. This absolute nothingness would contain no dimensions, no duration, no framework for existence of any kind. From this perspective, the question becomes, why does space-time exist, rather than there being no arena for existence whatsoever? This pushes us toward considering what could possibly bridge the gap between complete absence and the presence of a four-dimensional universe. The strongest form of nothingness would eliminate not just physical reality, but logical reality as well. No principles of reasoning, no mathematical truths, no possible worlds of any kind. This inconceivable absolute nothingness challenges our ability to formulate meaningful questions, since questioning itself presupposes logical relationships that would not exist in such a state. Yet some philosophers argue that only by contemplating this most extreme form of nothingness can we appreciate the full depth of the mystery of existence. Quantum mechanics offers one potential resolution to the something from nothing puzzle through the concept of spontaneous symmetry breaking. In quantum field theory, the vacuum state is not truly empty, but contains the potential for particle creation through quantum fluctuations. These fluctuations normally cancel out over time, maintaining the vacuum's overall emptiness. But under special conditions, quantum tunneling effects can cause spontaneous transitions from the empty vacuum to states containing real particles and energy. Some cosmologists have proposed that the entire universe represents one such quantum tunneling event, a spontaneous transition from absolute nothingness to the existence of space, time, matter, and energy. The probability of such an event might be infinitesimally small, but in an infinite expanse of nothingness, with unlimited time, even impossibly unlikely events would eventually occur. Our universe might be the result of a quantum fluctuation that created everything from nothing through natural physical processes. However, this quantum explanation faces the fundamental problem that quantum mechanics itself presupposes a mathematical framework, physical laws, and logical principles that must already exist for quantum tunneling to occur. We cannot use quantum mechanics to explain the origin of quantum mechanics itself. The theory assumes the existence of complex mathematical structures like Hilbert spaces, probability amplitudes, and unitary evolution operators. These mathematical entities must exist in some sense for the theory to describe how physical reality emerges from quantum processes. The mathematical universe hypothesis provides a different approach to the nothing-something question by eliminating the distinction entirely. If all mathematically consistent structures exist as physical realities, then nothingness becomes just another mathematical structure, perhaps the empty set or the null mathematical object. But this structure exists alongside all other mathematical possibilities, making it no more fundamental than any other form of existence. From this perspective, asking why there is something rather than nothing is like asking why there are numbers rather than no numbers. The question presupposes categories that don't apply to mathematical existence. Logical necessity represents another potential resolution to the ultimate question. Some philosophers argue that existence itself is logically necessary, that absolute nothingness is not just physically impossible, but logically contradictory. If this argument succeeds, then something must exist because the alternative is literally inconceivable. But this pushes the mystery back one level. Why should logical necessity favor existence over non-existence? What makes the logical structure of reality such that being is necessary while non-being is impossible? The principle of plenitude suggests that all possible ways of existing are actualized somewhere in reality. From this perspective, nothingness is just one possibility among infinite others, and it has no special claim to being more natural or likely than any other possibility. The fact that we observe something rather than nothing simply reflects the fact that we exist within one of the infinite possibilities where something rather than nothing occurs. This transforms the question from why something rather than nothing to why do we find ourselves observing something rather than observing nothing? But observers cannot exist to observe nothingness, so the question answers itself through anthropic reasoning. The role of consciousness in existence raises additional complexities for the nothing-something problem. Some interpretations of quantum mechanics suggest that conscious observation plays a role in determining which quantum possibilities become actualized. If consciousness participates in the creation of reality through measurement processes, then the existence of something, rather than nothing, might be partially due to the existence of observers capable of observing. This creates a circular relationship where consciousness helps create the reality that gives rise to consciousness. Recent developments in digital physics and simulation theory provide new perspectives on the fundamental existence question. If reality is fundamentally computational, then the question becomes, why are computations being performed rather than no computations occurring? This might be easier to answer than traditional versions of the question, since computation requires only abstract mathematical operations rather than substantial material existence. Perhaps the universe exists because mathematical computations are inevitable consequences of logical necessity. The theological dimensions of the nothing-something question have occupied philosophers and theologians for millennia. Classical arguments for the existence of God often hinge on the claim that existence requires explanation and that infinite chains of explanation must terminate in some necessarily existing entity. But even if such arguments succeed in demonstrating the existence of a necessary being, they leave unanswered why there should be any necessary being rather than the logical possibility of universal contingency. Some modern theologians have suggested that divine creativity operates not through adding existence to pre-existing nothingness, but through continuously sustaining the existence of everything that is. From this perspective, the question is not why something came to exist, rather than remaining nothing, but why anything continues to exist, rather than lapsing back into nothingness. This transforms creation from a historical event to an ongoing process that maintains the existence of everything at every moment. As we grapple with this ultimate question that seems to transcend all possible answers, we might discover that the mystery of existence is not a problem to be solved, but a fundamental feature of reality to be acknowledged and embraced. Perhaps the deepest truth is that existence needs no explanation because explanation itself presupposes existence, making the question of why there is something rather than nothing not answerable but revelatory of the absolute mystery at the heart of being itself. As we probe the deepest mysteries of cosmic origins, we encounter a profound puzzle that bridges physics and philosophy, the nature of consciousness itself, and its possible role in the emergence of reality. The hard problem of consciousness, how subjective experience arises from objective matter, becomes even more mysterious when we consider that conscious observers might not just witness cosmic evolution, but actively participate in its creation. Tonight, we explore the possibility that consciousness is not merely an accidental byproduct of cosmic complexity, but a fundamental feature of reality that plays an essential role in the transition from possibility to actuality. The hard problem of consciousness, first articulated clearly by philosopher David Chalmers, highlights the explanatory gap between physical processes and subjective experience. We can explain how brains process information, store memories, and control behavior, but we cannot explain why there is something it is like to be conscious, why there is inner experience rather than just outer behavior. This problem becomes even more acute when we consider cosmic origins. If consciousness emerges from matter, how can consciousness participate in the creation of the matter from which it emerges? Quantum mechanics provides the most direct connection between consciousness and cosmic origins through the measurement problem. According to standard interpretations, quantum systems exist in superpositions of multiple states until measurement causes them to collapse into definite configurations. But what constitutes a measurement? Some interpretations suggest that consciousness plays a special role, that conscious observation is necessary to transform quantum possibilities into classical realities. The von Neumann-Wigner interpretation explicitly assigns consciousness a fundamental role in quantum mechanics. According to this view, physical systems evolve according to the Schrödinger equation, maintaining quantum superpositions indefinitely unless they interact with conscious observers. When consciousness encounters a quantum system, it causes the wave function to collapse, selecting one possibility from the quantum superposition and making it real. This would make consciousness a creative force that participates in determining which aspects of reality become actualized. If consciousness plays a role in quantum measurement, and if the universe emerged from quantum processes, then consciousness might have participated in cosmic creation itself. This leads to paradoxical scenarios where consciousness helps create the universe that gives rise to consciousness. Such circular causation challenges our linear concepts of cause and effect, while suggesting that consciousness might be fundamental rather than emergent. The participatory universe concept, developed by physicist John Wheeler, proposes that observers are not external witnesses to cosmic evolution, but essential participants in its unfolding. Wheeler suggested that the universe doesn't just exist independently, but comes into being through observation. His famous delayed choice experiments showed that present observations can retroactively determine which quantum history actually occurred, suggesting that consciousness might participate in creating the past as well as the future. Panpsychist theories propose that consciousness is a fundamental feature of reality rather than an emergent property of complex matter. According to panpsychism, all matter possesses some form of primitive consciousness or experience, with complex consciousness emerging through the integration and combination of simpler conscious entities. If panpsychism is correct, then consciousness has been present throughout cosmic evolution, potentially influencing physical processes from the earliest moments after the Big Bang. Integrated Information Theory, IIT, developed by Giulio Tononi, provides a mathematical framework for understanding consciousness that might connect to cosmic origins. IIT defines consciousness as integrated information, the amount of information generated by a system above and beyond its parts. This framework suggests that consciousness corresponds to certain types of information processing patterns that could occur at any scale, from brains to potentially cosmic scale systems. The fine-tuning of physical constants for consciousness raises intriguing questions about the relationship between mind and cosmic origins. The precise values of fundamental parameters that allow complex chemistry, stellar evolution, and biological development also permit the emergence of information processing systems complex enough to support consciousness. This suggests either remarkable cosmic coincidence or some deeper connection between the structure of physical law and the requirements for conscious experience. Some interpretations of quantum cosmology suggest that consciousness plays a role in selecting which universe we observe from the infinite ensemble of quantum possibilities. If the universal wave function contains superpositions of all possible cosmic histories, conscious observation might participate in determining which branch of this cosmic superposition we experience. This would make consciousness a cosmic selection mechanism that helps determine the properties of the observable universe. The quantum Zeno effect demonstrates that frequent observation can freeze quantum evolution, preventing systems from changing states. Some theorists have speculated that cosmic consciousness, or widespread observation, might influence large-scale cosmic evolution through similar mechanisms. If conscious beings throughout the universe are constantly observing their environments, this could affect the rate of cosmic change and the direction of cosmic evolution. Consciousness might also influence cosmic origins through its role in creating meaning and purpose. If consciousness participates in determining which quantum possibilities become actual, then the values, goals, and intentions of conscious beings might influence the direction of cosmic development. This could create feedback loops where consciousness shapes the cosmos that shapes consciousness, leading to cosmic evolution that reflects the nature and aspirations of conscious observers. The relationship between consciousness and time adds another layer to these considerations. Our conscious experience of temporal flow, the feeling that moments pass and that we move from past to future, might not correspond to objective temporal reality. Some theories suggest that consciousness creates the illusion of temporal passage by comparing different brain states and constructing narratives about change. If consciousness participates in creating temporal experience, it might also participate in creating the temporal structure within which cosmic evolution unfolds. Recent developments in artificial intelligence and machine consciousness raise new questions about the role of consciousness in cosmic evolution. If artificial systems can achieve genuine consciousness, they might also participate in quantum measurement processes that influence physical reality. This could lead to scenarios where artificial intelligence systems affect cosmic evolution through their conscious observations and decisions. The possibility of cosmic consciousness operating at scales larger than individual beings, opens up even more exotic possibilities for consciousness-cosmic connections. Some theories suggest that galaxy clusters, black holes, or even the universe as a whole might possess forms of consciousness that operate on timescales and spatial scales far beyond human experience. Such cosmic consciousness could participate in cosmic evolution through mechanisms we cannot currently comprehend. The anthropic principle takes on new meaning if consciousness plays an active role in cosmic origins. Rather than simply observing a universe that happens to permit consciousness, conscious observers might participate in creating the conditions that allow their own existence. This could explain the apparent fine-tuning of physical constants without requiring vast multiverses or supernatural design. Conscious observers might participate in selecting the cosmic parameters that permit their own observation. As we contemplate the possible role of consciousness in cosmic origins, we're forced to reconsider fundamental assumptions about the relationship between mind and matter, observer and observed, subjective and objective reality. Perhaps consciousness is not just the latest development in cosmic evolution, but a fundamental feature of existence that has been participating in cosmic creation since the very beginning. In the deepest explorations of reality's foundations, a remarkable insight has emerged that might transform our understanding of cosmic origins. Information, not matter or energy, might be the fundamental substrate from which everything else emerges. The holographic principle suggests that all the information content of any region of space can be encoded on its boundary, implying that our three-dimensional reality might be a projection from information processed on a distant two-dimensional surface. This perspective opens up entirely new approaches to cosmic origins, where the Big Bang might represent not the beginning of matter and energy, but the moment when cosmic information first began organizing itself into the patterns we experience as physical reality. The it from bit hypothesis, proposed by physicist John Wheeler, represents one of the earliest articulations of information-centric thinking about cosmic origins. Wheeler suggested that reality emerges from answers to yes or no questions and bits of information that accumulate to create the appearance of substantial matter and energy. From this perspective, particles are not tiny objects but information patterns that maintain coherence through their relationships with other information patterns. What we call the physical universe might be the expression of underlying information processing operations. The holographic principle emerged from studies of black hole thermodynamics, where physicists discovered that the information content of a black hole is proportional to the area of its event horizon rather than its volume. This area-law relationship suggests that the information describing everything inside a three-dimensional region can be encoded on its two-dimensional boundary. Applied to cosmology, this principle implies that our entire observable universe might be a holographic projection from information encoded on a distant cosmic boundary. The ADS divided by CFT correspondence provides a concrete mathematical realization of holographic ideas. This remarkable duality demonstrates that string theory in a five-dimensional anti-de Sitter space is exactly equivalent to a quantum field theory on its four-dimensional boundary. Everything that happens in the bulk five-dimensional space, including gravitational dynamics, black hole formation, and space-time geometry, can be completely described by field theory on the boundary. This suggests that higher dimensional physics might be emergent from lower dimensional information processing. Applied to cosmic origins, holographic ideas suggest that the Big Bang might represent the beginning of information processing on a cosmic boundary, rather than the creation of matter and energy in a three-dimensional space. The expansion of the universe would correspond to the growth of computational complexity on the boundary, while the cooling of the cosmic background radiation would reflect the organization of boundary information into increasingly structured patterns. Quantum error correction provides another connection between information theory and cosmic origins. Recent research has revealed that the emergence of space-time from quantum entanglement patterns resembles the operation of quantum error correcting codes. Just as these codes protect quantum information from noise and decay, the geometric structure of space-time might emerge from quantum information patterns that automatically maintain their coherence. This suggests that space-time itself is a form of information storage and processing system. The relationship between quantum entanglement and space-time geometry has revealed deep connections between information and cosmic structure. When regions of a quantum system become entangled, they create correlations that appear to generate geometric connections in space-time. The more entangled two regions are, the closer they appear to be geometrically. This suggests that the fabric of space and time might emerge from underlying patterns of quantum information correlation. The second law of thermodynamics and the growth of entropy provide another information-theoretic perspective on cosmic evolution. As the universe expands and cools, its total entropy increases, representing a growth in the amount of information needed to describe cosmic structure. This information growth might be fundamental to cosmic evolution, with the arrow of time pointing in the direction of increasing information content and complexity. Black hole information paradox illustrates the deep connections between information, conservation, and cosmic origins. When matter falls into a black hole, quantum mechanics insists that the information it contains cannot be destroyed. But general relativity suggests that this information disappears when the black hole evaporates through Hawking radiation. The resolution of this paradox might require understanding how information is preserved and transformed during extreme gravitational processes, potentially illuminating how information behaves during cosmic creation events. The holographic principle suggests that cosmic horizons, boundaries beyond which we cannot observe, might be fundamental information processing surfaces, rather than mere observational limits. Our cosmic horizon, which represents the edge of the observable universe, might be the boundary on which all cosmic information is encoded. The physics we observe within this horizon would be projections from information processing on the boundary itself. Digital physics takes information-centric approaches to their logical extreme by proposing that the universe literally is a computation. In this view, cosmic evolution represents the execution of a vast algorithm, with each moment corresponding to a computational step and each physical process corresponding to an information transformation. The Big Bang would represent the initialization of this cosmic computation when the program first began executing. The relationship between information and consciousness takes on special significance in holographic approaches to cosmic origins. If consciousness emerges from specific patterns of information processing, and if the universe itself is fundamentally information theoretic, then consciousness might represent the universe becoming aware of its own information content. Conscious observers would be information patterns that have become complex enough to model other information patterns, including themselves. Loop quantum gravity provides another framework where information plays a fundamental role in cosmic origins. In this approach, space and time are quantized into discrete informational units. The Big Bang represents a moment when quantum geometric information transitioned from one configuration to another, possibly through a bounce that preserved information from a previous cosmic epoch. The discrete structure of quantum geometry naturally provides a framework for information, storage, and processing at the most fundamental level. Vacuum fluctuations and virtual particle creation can be understood as information processing events, where the quantum vacuum computes the probabilities for different particle configurations. The uncertainty principle prevents the vacuum from having zero information content, ensuring that it continuously processes information about possible particle states. Universe creation might represent moments when this vacuum information processing produces persistent information patterns that we interpret as matter and energy. The measurement problem in quantum mechanics takes on new meaning in information-centric approaches. Rather than asking how observation causes wave function collapse, we can ask how information about quantum systems gets integrated into larger information patterns. Measurement might represent information integration events where quantum information becomes incorporated into classical information structures. Artificial intelligence and machine learning provide new tools for understanding how complex information patterns can emerge from simple rules. As AI systems become more sophisticated, they demonstrate how information processing can generate apparent understanding, creativity, and goal-directed behavior. This suggests that cosmic information processing might naturally give rise to complexity and consciousness without requiring additional non-physical ingredients. As we contemplate the possibility that reality emerges from information processing rather than substantial matter, we begin to appreciate how cosmic origins might be fundamentally computational rather than material. The Big Bang might represent not the creation of stuff, but the beginning of processing the moment when cosmic information first began organizing itself into the patterns of relationship and correlation that we experience as space, time, matter, energy, and ultimately consciousness itself. As we stand at the threshold of a new era in cosmology and fundamental physics, the question of what existed before the Big Bang is being transformed by revolutionary observational capabilities and theoretical insights that promise to penetrate deeper into the ultimate mysteries than ever before. The next few decades may bring discoveries that either resolve these deepest questions or reveal that they transcend the boundaries of scientific inquiry entirely. Tonight, we explore the cutting-edge research programs and emerging technologies that might finally illuminate the darkness beyond the cosmic beginning, or teach us why some mysteries are more beautiful than any answer could be. Gravitational wave astronomy represents perhaps our most promising new window into the earliest moments of cosmic history. The LIGO and Virgo detectors have already revolutionized astrophysics by detecting ripples in space-time from colliding black holes and neutron stars. But future gravitational wave observatories might detect much more subtle signals from the primordial universe itself. Gravitational waves generated during cosmic inflation, phase transitions in the early universe, or even the collision between bubble universes in eternal inflation scenarios. The proposed space-based gravitational wave detector, LISA Laser Interferometer Space Antenna, will be sensitive to much lower frequencies than ground-based detectors, potentially revealing gravitational wave signatures from cosmic strings, first-order phase transitions, or the merger of primordial black holes formed in the early universe. Even more ambitious concepts like the Einstein telescope could detect gravitational waves from the epoch of recombination itself, providing direct observational access to cosmic events occurring just hundreds of thousands of years after the Big Bang. The cosmic microwave background continues to yield new insights into primordial physics through increasingly sophisticated polarization measurements. The Planck satellite provided our most detailed map of temperature fluctuations in the cosmic background radiation, but future missions will focus on the subtle polarization patterns that could reveal the gravitational wave signatures of inflation. The detection of primordial B-mode polarization would provide smoking gun evidence for cosmic inflation while constraining the energy scale at which inflation occurred. Advanced cosmic microwave background experiments, like the Simons Observatory and CMBS-4, will search for signatures that could distinguish between different inflationary models or reveal evidence for more exotic scenarios, like cyclic, cosmology, or bouncing universe models. These observations might detect the subtle imprints of quantum gravity effects, extra dimensions, or even collisions with other bubble universes that occurred during our cosmic infancy. Precision cosmology, through large-scale structure surveys, is revealing the distribution of matter throughout cosmic history with unprecedented detail. Projects like the Dark Energy Survey, the Large Synoptic Survey Telescope, now Vera Rubin Observatory, and the Euclid mission are mapping billions of galaxies to trace how cosmic structure has evolved over the past 13 billion years. These observations constrain models of dark matter and dark energy, while potentially revealing signatures of modified gravity or extra-dimensional effects. The study of primordial black holes offers another avenue for probing physics beyond the Big Bang. If quantum fluctuations during inflation occasionally created regions dense enough to collapse into black holes, these primordial black holes would preserve information about conditions in the very early universe. Recent gravitational wave detections have revealed populations of black holes with unexpected masses that might have primordial rather than stellar origins. Neutrino astronomy is opening new windows into cosmic history through particles that interact so weakly with matter that they can travel through the universe largely unimpeded since the earliest moments after the Big Bang. The cosmic neutrino background, predicted to exist as a relic of Big Bang nucleosynthesis, has never been directly detected, but would provide information about conditions when the universe was less than 1 second old. Future neutrino detectors might even detect relic neutrinos from cosmic inflation itself. Laboratory experiments in quantum gravity are beginning to test fundamental assumptions about the nature of space and time at the smallest scales. Experiments with ultra-cold atoms, trapped ions, and other quantum systems are creating analog models of curved spacetime and black hole physics. These tabletop experiments might reveal signatures of discrete spacetime, extra dimensions, or other exotic effects predicted by quantum gravity theories. High-energy particle physics experiments continue to probe the fundamental structure of matter and energy under conditions that might illuminate cosmic origins. The Large Hadron Collider has explored energy scales approaching those present in the early universe, searching for extra dimensions, supersymmetric particles, and other exotic phenomena. Future colliders, like the proposed Future Circular Collider, could probe even higher energy scales where quantum gravity effects might become apparent. Artificial intelligence and machine learning are revolutionizing how cosmologists analyze vast datasets and explore theoretical possibilities. AI systems can identify subtle patterns in cosmic microwave background data that human researchers might miss, simulate complex cosmic evolution scenarios, and even generate new theoretical frameworks by identifying unexpected connections between different areas of physics. These tools might accelerate discovery of signatures from beyond the Big Bang. The role of consciousness in cosmic origins remains one of the deepest frontiers for future investigation. As our understanding of consciousness and artificial intelligence advances, we might develop new insights into the role that observation and information processing play in the emergence of physical reality. Quantum computing experiments might reveal whether consciousness has special properties that affect quantum measurement processes. Astrobiology and the search for extraterrestrial intelligence add another dimension to cosmic origins research. If consciousness is common throughout the universe, then advanced civilizations might have developed insights into cosmic origins that transcend our current understanding. The detection of obviously artificial signals or structures might provide clues about the deepest nature of reality from perspectives we cannot currently imagine. The philosophical implications of cosmic origins research extend far beyond technical physics and astronomy. As we probe deeper into the ultimate nature of reality, we're forced to confront questions about the relationship between mathematics and physical existence, the role of observation in creating reality, and the meaning of existence itself. These investigations might reveal that some questions transcend the boundaries of scientific method while remaining central to human understanding. International collaboration is becoming increasingly important as cosmic origins research requires resources and expertise that no single nation can provide. Projects like the Event Horizon Telescope, which created the first images of black hole event horizons, demonstrate how global cooperation can achieve observations impossible for individual institutions. Future investigations of cosmic origins will likely require similar levels of international coordination and resource sharing. The ethical implications of cosmic origins research are beginning to attract attention as these investigations touch on fundamental questions about existence, consciousness, and the nature of reality itself. If research reveals that we live in a simulated universe, that consciousness plays a role in creating reality, or that the multiverse contains infinite copies of ourselves, these discoveries would have profound implications for how we understand moral responsibility, personal identity, and the meaning of life. Educational and public outreach efforts are crucial for helping society grapple with the implications of cosmic origins research. As these investigations probe the deepest questions about existence itself, their results will inevitably challenge conventional wisdom about the nature of reality. Preparing the public for potentially revolutionary discoveries requires careful communication about both the scientific evidence and its philosophical implications. The convergence of multiple research programs, gravitational wave astronomy, cosmic microwave background studies, particle physics, quantum gravity experiments, artificial intelligence, and consciousness research suggests that we might be approaching a period of rapid progress in understanding cosmic origins. The next few decades could bring discoveries that either answer the ultimate questions about what existed before the Big Bang, or reveal why such questions transcend the boundaries of scientific inquiry. Yet perhaps the most important insight emerging from our exploration of cosmic origins is the recognition that mystery itself might be a fundamental feature of existence. The questions we can ask about the deepest nature of reality might be more profound than any answers we could discover. The capacity to wonder about cosmic origins might be as remarkable as the origins themselves, evidence that the universe has given birth to minds capable of contemplating their own cosmic context. As we prepare for the discoveries that await us, we're reminded that the greatest truths about existence might not eliminate mystery, but deepen it. Each answer we discover about cosmic origins reveals new questions that push the boundaries of understanding ever further into the unknown. The question of what existed before the Big Bang might ultimately teach us not just about cosmic history, but about the relationship between knowledge and wonder, between understanding and awe, between finite minds and infinite mystery. The future of cosmic origins research promises to be as extraordinary as the questions it seeks to answer, carrying us ever deeper into the fundamental nature of existence itself.